Hi, in this video, we will understand about Monte Carlo simulation and its specific use in finance, its benefits in modeling uncertain events. Finally, we'll get down to coding it and visualizing the results. So this topic is part of our financial computation course, and hence it is assumed that the learner is already proficient with Python, understands probability distribution, basic statistics, and random variables. Even for non-coders, the algorithmic logic should be quite intuitive and it follows concepts from maths, which is covered up till class 10. So Monte Carlo simulation is a mathematical technique which is used to estimate the possible outcomes of an uncertain event, and it is widely used in events of chance like game theory, operations research, even in physics, finance, and in many other fields. It was invented by John Newman and Stanislaw Ulam, these two individuals, while they were working for the Manhattan Project during World War II, primarily to improve decision making under uncertain conditions. And Monte Carlo analysis or Monte Carlo simulation, it involves running many different scenarios with different random inputs and then summarizing the distribution of the results. And it will become quite intuitive when I'll probably turn to a sketch which I drew for this session. And in this specific video, we'll be using Monte Carlo simulation to generate a series of simulated stock prices from the random walk events. And for doing so, we will consider India's frontline stock index called Nifty 50. And for those of you who do not know what a random walk event is, it's very simply a time series where the current observation is equal to the previous observation with a random step up or down. Like a stock generates a random return the next day, which could go up or down by a certain magnitude. And these simulated stock prices give us an idea of the estimated stock returns we can gain while bearing a certain degree of risk. So let's try to make this a bit more intuitive. Yeah, I hope this is very clear and visible. So we have two axes here, X and Y. On the Y axis, we have prices. On the X axis, we have days. So let's say we want to look 10 days ahead and get an idea of what is going to be an estimated range of our stock from the current point. So let's say the current level of stock is here where my cursor is. And let's try to figure out, get a sense of where the stock might be within a probable range over a period of, let's say, next 10 days. So the way we are going to work with is we'll do a random walk, which is that the price on the day one of prediction will be the price on the previous day plus a random return from a normal distribution. And this random return, which we're generating from a Gaussian distribution or a random distribution, will bear the statistical property of our input function, which is the price. So let's say we are taking price over the last 6 months, whatever are its central tendencies, let's say the mean and its standard deviation, which represents the volatility. We will generate a random distribution out of these two statistical variables. And from that standard random normal distribution, we will generate a random return on a daily basis. So we start on, let's say, day 0, go to day 1, and we'll generate the price on day 1 as a function of day 0 price plus a random return. And like this, we'll go to day 2, where we'll use the price on day 1, and we'll generate a return on day 2 for the price of day 1. Likewise, on day 3, we will generate a random return for the price of day 2. And like this, over a period of 10 days, let's say the price takes a particular path, which is here. Now, if we do yet another trial, it may take a very different path, let's say like this. Because ultimately it's generating random returns on a day-by-day basis. And over a period of 10 days, it is generating a random path. So if we run this trial, let's say 10,000 times, it will generate 10,000 possible paths, which the price can take starting from the current price, and every single day, right? It is taking a random return over the previous day's price. And these random returns are coming from a normal distribution, a random normal distribution bearing the statistical tendency of our input function. So when we do this trial over, let's say 10,000 times, right? it gives us all possible combinations of price paths over the period of prediction, which in this case is 10 days. And from that, we can say, okay, if our confidence interval is, let's say, 84%, where do we get 84% of price occurrences? What is the range within which we get 84% of our price occurrences? So we will get something like this, right? If we have, let's say, 10,000 price paths and we plot where are we getting 84% of the observation, we will get a range something like this. So if we take 84% confidence interval on the higher side, it will say that, okay, from this price level, 84% of all price paths were below this price level. Similarly, we can take 100 minus 84 or the 16% confidence interval, and we'll say that 84% of all the price paths were above this. So there is a 16% of error on the upper side, 16% of error on the lower side. And this range will represent, let's say, 68% of potential occurrences if this price were to take many different random paths over a period of this prediction period. All right. That said, let's get down to coding it step by step, and it will become clear as we go along. So I'm going to import a few scientific libraries. First is pandas, import pandas as pandas. I will also import NumPy as NP. I will also be using a visual library called matplotlib.pyplot as PLT. And let me import another library called. Okay, so I have these 4 libraries. Now I already have Nifty prices, and we will try to extract the Nifty prices. So I'm going to say pd.read_excel. I'll define the path where my file is. Will be users. Okay. Let's see if you got that right. Yes. So I'm going to make one change here. I'll say I'm going to set the index here. And I will say that the column with the title date should be my index. And now we should be good to go. And there you go. So I've got prices up till 28th of June. So now I will define the start date from where we want to start our simulation data, or from the time from which we want to take our input function, which is the backdated prices of Nifty, so that we can compute its mean and standard deviation. So I'm going to take the prices over the last 6 months. So here I will define the start date as 2023-01-01. My price data will become specifically the close price, starting from the start date till the end. My last price will be price data log -1. And I will define my confidence interval as 84. So 84 here represents the price level below which 84% of price occurrences will occur. Represents the price level below which 84% of price occurs. Or let me say price level below which 84% of price paths will occur. And converse of this will be CI equal to 100 minus 84 equal to 16. And I will set my prediction period for here as 10 days ahead, which represents how many days ahead we wish to predict. Okay, so far so good. Now, first, let's just write a function to compute the returns and volatility from our input function. So I'm defining the function as returns and volatility. I will pass my price data in this. And I will say returns is equal to price data dot percentage change on a daily basis. What this gives me are the daily returns, but in decimal. Then I can compute the returns mean. It will be simply the variable returns. Its mean. And I will take the daily volatility, which I'll assign to a variable called daily vol for short. And I will take the standard deviation of daily returns, which will again be a figure in decimal. Standard deviation in decimal. And let's say if our volatility, which is one of the key determinants of our price ranges fluctuating over the prediction period, let's say we are currently operating on whatever has been the historical volatility over our period of consolidation, which is the last 6 months from the starting of year 2023. What if this volatility changes, which is the input determinant for all the random variations, for all the random values for predicting our daily returns? If that changes, right? So we can have a little bit of flexibility here. What I typically like to do is, I typically like to consider a volatility amplifier. Okay, we are operating with the current volatility, but what if suddenly there is a change of event and this volatility gets amplified? We're usually not worried about the volatility getting de-amplified. Like, for example, if the volatility is right now 10% or 11%, if it becomes 9%, it usually points to a very stable market. So we are not very concerned about that. That's a good situation to be. But the markets tend to turn very choppy or very volatile if suddenly the volatility gets amplified. If it increases by 10%, 20%, 30%, 40%, or even 50%. Like in the prelude to the first week of March 2020, the volatility suddenly amplified by more than 100%. So it's good to have some kind of a volatility amplifier and see how our volatility will play out under different volatility amplification scenarios as well. So this is something which we'll keep dynamic. So we'll enter an input function and we will say that enter your volatility amplifier in decimal. I can keep it 0, wherein I say, okay, you know what, we'll stick with the current volatility, which we will do any which ways. But what if the volatility goes up by 10%, which is represented by 0.1 because we are taking the figures in decimal, or let's say by 20%, or by 30%, or by 40%, or by 50%. So we'll keep it up to 50%. So this will always prompt us that what is the volatility amplification do we want to define in our returns and volatility computation function. And we can pretty much keep it at 0 to stick with what we have. And it will give us the daily volatility as daily volatility into 1. Okay, it will be daily volatility into 1 plus take a float of whatever the volatility amplification factor. And last price is, okay, fine, it's anywhere defined. Last price is equal to this data. Okay, so that's our function. We have computed returns, daily returns, which will be a time series. We have computed the mean of returns. We have computed the daily volatility, and we have the last price. Okay, let's call our function. We have pass our price data and see if you're okay so far. Okay, so it's prompting me for entering the volatility amplification. Currently, I'm keeping the amplification as 0. We will stick with the current volatility. And I get an error. Let's see what does the error say. Okay, so yes. So that's our daily return series. The second figure will represent our returns mean. Then we get the daily volatility and the current price, which is the last price in the time series. So fine, we have this function so far. Let me just name this file. Name it as Monte Carlo for Nifty 50. And save our work so far. Okay, so we have our first function. Now, we will define our first Monte Carlo function. We will break down the whole process into multiple functions to make it simpler to code and to make it simpler to check the code and debug if there is any bug. So I will pass the price data. I need another parameter, which is the prediction period. Okay. And now I will call the first function, which I've already defined, returns mean, daily volatility, and the last price. I will call it from the function which we've already defined above, returns and volatility We price, and we'll pass the price data as an input function. Now, I will define a parameter, a variable called number of simulations, the number of trials, which I will keep fixed as 10,000. So we will have 10,000 trials, and we will compute the various possible paths the price can take over the 10-day predicted period over each and every trial, and 10,000 such trials. And we will capture these price paths in something called simulations data frame. So let me define an empty data frame for this. Then for X in the range, the number of simulations we have, we will begin with our counter at 0. And this counter here represents the count of the trial from 0 all the way to 9,999 for a total of 10,000 trials. And for each trial, we want to capture the price path in a list variable called price series. We will also capture the corresponding returns. So we will have a return series. And because the very first input in the return series is a NaN here, which you can see, which is not a number. So we will set this as 0. Now, what it will do is it will draw random samples from a normal or a Gaussian distribution with our given mean and volatility of the input function. Volatility here will be the standard deviation. And here we are introducing randomness of daily returns, which will influence the current price over previous day's price. Instead of taking mean as 0 for the normal distribution, we take mean of our input function, which is the price series. And why do we do this? To induct the statistical characteristics of our input function, which in this case is Nifty 50 closing prices over last 6 months. I hope it's clear so far. So our next step is to compute the current price, which will be the first predicted price on day one of our prediction period. So we take first the last price. We do into 1 plus, that is the previous day's price, plus a random return, which will come from a random normal distribution contained within the NumPy library. And for this, we want to have this normal distribution taking the mean as our returns mean and standard deviation as our daily volatility. And the corresponding return will be simply the price that we get over the previous day's price. Okay. -1. To 100. Okay, that becomes our current return. And we will append this to our price series. Now, okay. So we are still at the very first trial. Our count is still 0. And we now have to run this over the entire, for first trial and for each and every trial. We want to run the simulation over the entire predicted period, that is over the next 10 days, or whatever is our predicted period range. So we will run another for loop for that. So for y in the range prediction period, so what we are doing here is within each trial, we find the price path for the prediction period. And if count equals to the prediction period -1, then we break our function. And why am I saying prediction period -1? Because the prediction period is 10 days and the count is going to run from 0 all the way to 9 for 10 predicted values, with the number 10 not being included. All right. So for each y, we will compute the price, which will be price series. The last price will be the price series count into 1 plus drawing a random normal return. Random dot normal. I made a mistake here. Returns mean and daily volatility. And similarly, return will be same as above. I hope this is very clear. I will explain this once again as to what's going on here. So here I append these prices, or append the latest generated price. Return series again will append the latest return. And my counter will go up by 1. And when we are done, we'll have a simulations DF for X, which is my iterator here. After I complete the first trial, it will be assigning the price series. That is the price path for that trial against the first trial in my data frame simulations DF, which I defined at the start. And same for returns. Simulations DF. I will have another column here which will capture the corresponding returns. So let's call it returns plus string of the count number. And this will capture the return series. Then I simply return the data frame. Okay. Let's try to call our function. I have to pass two parameters here. One is the price data, second is the prediction period, both of which I have defined above. We've defined these parameters here. So let's call our function. Okay, it's asking for the volatility amplifier because we have passed the returns and volatility function within this function. I'll keep it as 0. And then I want to see what my simulations look like over the entire predicted period. So while this is running, let's just quickly go through this function again. We first call in our returns and volatility function to capture the returns, the daily return series, the mean of the returns, the daily volatility, and the last price. Then we want to run 10,000 trials. So we define it as a parameter number of simulations. We define an empty data frame where we want to capture all our simulation results. And then we run 10,000 trials. So X, which is an iterator for the number of trials, X in range, the total number of trials. And for each trial, now we are in the each trial, right? We want to capture the whole price path, which is generated in that trial, and the return series, which is generated against that trial. So we go and we capture the next price, which will be the previous price plus a random step up or down over the previous price, which will come from a normal distribution of our returns mean and daily volatility. And like this, now we will go over the entire predicted period. So within the trial, in the first trial, we'll go through the entire predicted period or the entire prediction period to generate our price path for that trial. For that, we'll go into another for loop where the iterator we are calling y, and y is going to run over the range of the entire prediction period, and it will keep generating price at each step. The next price at each step, again, a function of the previous price and a random return up or down over the previous price. And once it completes this entire price path, which is appended into this price series, what it will do at the end of it is it will assign that price series for that trial in the data frame against that trial number. And correspondingly, the return series will be assigned to the to the column called return for that particular trial in the data frame. And then we're going to run this X all the way till X completes 10,000 runs. And for each of the run, we'll be capturing similar price series and return series. And this is what we get. So if we take a look at this, we have 10 rows. For each trial, right, 0 is representing the trial number. For each trial, right, we are generating the predicted prices over the prediction period. And 0 represents the first day of the trial or first day of the prediction period. So we have 10 such inputs here, each generated randomly over the input function. And on the column side or on the right hand side, we are going to see 10,000 values or 9,999, which represent the trial. So each of the column represents a trial, and each of these rows represent the various days over which the trial is taking place, which is our prediction period. So now that we have our simulation results, let's just visualize what does our simulation look like in different trials. So let's take trial number 0 and plot it. And I will do a grid here as well. And I will try to so let's say this is in one of the trials, this is the price path. Now let me take the 100th trial. I generated this price. Let me take the 1000th price path. It generates a different price path. Let me take the result from, let's say, 21st 100th trial, and we get yet another price path. Let me go to the 900th trial. So for different trials, we are getting different price paths. There you go. So now that we have our simulation results,